next presentation. Go long, sending weird signals long distances over existing optical infrastructure. I would like to introduce Ben Cartwright-Cox. Please come to the lectern. We'll be presenting Go Long. Ben runs bgp.tools and traveled from London to join us today. Sorry, let me move to the other side so you're more comfortable with your driving position.
What? Oh.
This is your third time presenting according to my notes. Your first talk was called Discovering Flaws in BGP Error Handling, which was at NANOG 89 in San Diego a year ago. Wow. Welcome back. It's a pleasure to have you with us. There will be Q&A at the end. Enjoy.
Thank you very much. So, hello everyone. My name is Ben. You may know me from things like bgp.tools, which is a looking glass thing, which has also like monitoring services. If you're interested in that, check it out. It might be interesting. I also did BGP battleships. Last year, I also presented on doing weird things of SFPs with computers inside them, and a bunch of DOS exploits. Anyway, the truth is I really like knowing how things work. It makes life more interesting knowing how stuff works, but also there's like they generally fall into two categories, right? If something is kind of interesting and you don't know how it works, it's either incredibly smart or really stupid. I'd like to know which one it is before I deploy it. Talking of that, optical stuff is everywhere. As long-haul networks or in short-haul networks, we've gotten pretty used to sending stuff over optical fiber. And you know, optics is a weird world. You have like the device protocols, the stuff that like comes out the physical gold finger. You have the actual optic types and weird shapes and form factors, and then you have the sort of transmission wavelength, the types of photons and how you wobble the photons across the system. So the average boring network is, well, pretty boring. It uses an SFP port on the switch, using probably a vendor optic or a third-party supplier. There are, like, as far as I understand, 5 factories that actually make optics, and the rest is just a giant pile of who gets to take the markup and who gets to support you when you send a ticket in when it doesn't work. Yeah, the switch just shoves out an XGMOI signal, and then the optic does something to turn that signal into laser light. The opposite happens on the other end. Data bits are exchanged, cat videos are exchanged, or whatever things people do with their internet. I don't want to know sometimes. So some optics are surprisingly stupid. So your average optic is not really doing much thinking. We're going to briefly gloss over the optics that have full CPUs in them. Last year I presented on some of this. It turns out when you present optics that have computers in them, people come at you with more weirder optics that have computers in them. So I did enjoy this VDSL modem in an SFP, which also runs Linux in the background because why not? But anyway, most optics are surprisingly stupid. With some other caveat. Obviously, optics have an EEPROM inside them so that the switch can tell what you just plugged in. It also allows the switch to be picky with the vendor that you plugged into it and ask you to pay more markup for sort of the same thing. But you know, and also most optics these days have a tiny microcontroller in them that allows you to see, you know, the light levels and various other bits and bobs. So that's, you know, pretty useful. The average faster, more modern boring network will use QSFP port 28s on a switch with probably, once again, a vendor optic, depending on the optic, because 100 gig is a complete mess, uses various fancy chips to convert signals into various different things. Maybe, if you're lucky, something even coherent, like LR1. The opposite happens on the other end. Data bits exchanged. Cat videos, or whatever people are doing with their connection, are at higher speeds or at higher capacity. So these optics sometimes can be surprisingly smart. So the nice ones have things that will turn these 4 lanes of 25 gigabaud into one beam of 100 gig. This is mostly sometimes required, you sometimes require pretty advanced chips to do this. Like if people in the crowd have Intel laptops, these optics often have chips with smaller process nodes than the chips that are in your laptop. These things also consume a considerable amount of power, and the power draw isn't as much of a concern as much as the heat output of these things is a concern. Depending on the type of optic, once again, 100 gig is a complete mess. You know, at the complexity, price, ups, downs, that's a complicated world. Other optical form factors are available, of course. There's the XFP for the original 10 gig stuff, CFP for thicker 10 gig stuff, various QSFP like variations, depending on like double density, stuff like that. There's the newer OSFP, which as far as I understand is more and more required for the 800 and 1.6 tera stuff. X2 if you're legacy, Zenpack if you're even more legacy. These have all been used in various places, but similar enough not to really make a difference here. There's also, of course, the home theater stuff, which uses a different kind of optical transmission. That's SPDIF and Toslink. So Toslink, briefly talk about it. There are two kinds of people who use Toslink. One, that people who have ground loop issues in their system, and that is people who, that's basically main speaker hum at 50 or 60 hertz, depending on where you are in the world. And the other people who just want to seem cool by having real optical stuff in their home. This is a pretty rudimentary system. It maxes out at about 10 megabits per second. Realistically, most stuff is, if it's stereo audio, it's 3 megabits. The wavelength is basically just a red LED, and the cables have like this super thick 1 millimeter plastic core. And seemingly, if you buy them from eBay, all of them are gold-plated, which is, sure, I guess. Don't think about it. So critically, though, they quote, the maximum length of the cable is 10 meters. And the 10 meters is almost always because these giant 1 millimeter plastic core cables basically just mash the signal when you get more than 10 meters in. So I was thinking. So these things are clearly not very smart, right? They're too stupid to care about what goes into them. No real brains are happening here. So, this thing is also too stupid to care. 10-kilometer Toslink? So, we're going to have to do some things. So this is the back of the Goldfinger on an SFP optic. I have censored out a couple of these things here because these are for the microcontroller. We won't need the microcontroller for where we're going. We don't care, so yeah. You'll also notice that the power supplies have two different, so the receive and the transmit side have different power supplies. This is how your switch knows the current required on each end, so the switch is the one that's measuring that. And also that the transmit and receives also have their own negative and positives, which is interesting. We'll get into that in a sec. We're going to cheat a bit because I don't particularly want to spend all of my time designing PCBs. The lovely folks at Osmocom have an SFP experimenter board, which is effectively just a small board which comes with a couple of nice things. Critically, it's a 5 volt to 3.3 volt power supply, because that's the voltage that these optics operate on. It has an SFP connector and cage. It's got a bunch of these pins broken out for you. Also a load of LEDs that tell you when you've upset the optic. We'll be blowing up one optic in this entire experiment. Yeah, and a bunch of big exposed pads for you to inject your signal. And also, critically, a pair of line drivers to drive the optic. Now, why do we need that? So line drivers, the best way I can describe it, they just make things wobble right. So this is your standard digital-looking signal. It can be most forms, TTL, whatever. So this is what a line driver does. It turns it into a differential signal. Now, you want to do differential signals because they work much better over hostile environments. So if you're clocking these things at like really high speeds, especially if you're next to other very high speed things, once you hit the 100 megahertz spectrum, at some point every wire doesn't actually want to keep things in the wire. They like to be antennas instead. And so if you use differential signaling, you can counteract some of this interference. So this is roughly speaking what audio looks like when it goes onto a, just from a scope screenshot. Okay, I don't understand why the ordering was there, but we'll ignore that. So yeah, audio in, on the same scale, SPDIF out. Very different time scale, but you've got your very clear digital signal there. And it's about 2 megahertz of data if we really go for it. So the proof of concept. So I'm going to play some music on my laptop. I'm going to shove it into a Toslink analog to digital converter that I bought off eBay. This thing puts out a surprisingly high amount of voltage, so I shift it down, shove it into the SFP, loop it around some multi-mode cable that I found in the bin, and then we put it back into the optic, DAC to my headphones. It's not particularly TSA friendly looking, but it does work. So it adds about 34 nanoseconds of latency, 2,000 kilometers a second. That means it's about 680 centimeters, which is pretty good going. So the patch cable that I got off the bin was about 5 meters. And so yeah, this is a viable thing. So what if we could make it go long haul? So I live in London, as you might be able to tell from the accent. So Telehouse is one of the big campuses in the Dolan Docklands. There's also a smaller, slightly cheaper data center around the corner. A friend has presence in both, so I got to borrow their CWDM MUX. So thank you for James for being trusting enough for me to plug some random stuff into their equipment. So I put an optical loopback on the Telehouse side because I didn't want to be there, and got a crash cart inside the other side, IP house. So this is roughly speaking what it looks like. And it worked. The portable speaker obviously is struggling a bit in the data hall, but critically, it did not blow up the relatively expensive CWDM optic, and the thing actually worked with almost no issues. On the scope, it's a little harder to see because you have to zoom out a bit, and there's no easy way of aligning your signal, so you have to sort of squint and figure out where what the actual latency is. But the latency comes out to something like 11 microseconds. Now, at the speed of light, plug that into Wolfram Alpha, it's about 2.2 kilometers. Which is cool. So the fiber is actually, despite the data center sort of plotting it out on Google Maps being only about 630 meters away in terms of walking distance, is actually about 1 kilometer away in terms of fiber, which makes sense because buildings aren't 2D. And especially a building like Telehouse, multiple floors, multiple risers, bit of chaos. But what if we could go longer haul? So longer haul options. Typically, if you were doing 1 or 10 gig, if you're going really long haul, you would be using DWDM at this point. Dense DWM is like CWDM, but denser. It's in the name, it's in the acronym. 8 channels to 32 to 64. And the optics are a little bit more expensive because they use some interesting physics inside of them, mostly around temperature control, as far as I understand. You can also amplify them much easier to get even more distance. There's some caveats here. If you're borrowing someone else's MUX, you have to make sure that you're putting in the same level of brightness as other people. Otherwise, the amplifiers do some weird things. Side note, if you ever look at how an F2 amplifier works, kind of feels like a bug in physics, but I'll glance over that as well. Most people who are selling waves, obviously you don't want customers to use your multiplexer directly. As mentioned, if you are not balancing your light inputs, weird stuff happens and you don't want one customer to knock out everyone else. So this is where you use a transponder. Transponders are something that basically copy and pastes a signal from one SFP port to another. It doesn't think about it, it just copy and pastes it. The idea is that you can provide someone a 1310 nanometer, which is commodity, and then you can plug whatever you want in on their end, and they don't have to go and do some weird DWM stuff. So my weird signals work completely fine in transponders, as they are pretty dumb devices. The incompatible options are muxponders. So muxponders and other fancy line systems do a lot more processing with the input signal. These devices obviously have great density and are really attractive if you've got a particularly long run bit of fiber or very expensive bit of fiber, depending on which region you're in. But they do this by understanding the signal that comes in. So they have a larger awareness of things like Ethernet, fiber channel, InfiniBand sometimes, and they merge these things into higher speeds. So for example, a muxponder can have like an entire face full of 10 gigs and stick it out into a 200 gig single signal. So I can't send Toslink over this because these things will not understand, well, these things don't know how to think that slow. But they also just don't understand that kind of signal. They're expecting Ethernet frames. Thanks to Lonap, they had a spare DWDM channel between Equinix LD6, which is Slough, and LD8, which is London. This is not only intercity, but it also has to be amplified, which is cool if you can survive amplification. Estimated, well, their estimates is it is about 73 kilometers away. So for you not familiar, so this is roughly speaking what I think the path is. This is the border of London. So as we know, Slough is definitely not London. I say this because most of Equinix's London sites are in Slough. Definitely not London. But anyway, so this is what the stack looks like. You'll notice that there is a attenuator there. That's because their side has a EFTA MUX, EFTA DWM MUX, and so you have to these things, because you have to balance the signal going into this thing, the signal comes out pretty bright. And so if you're just doing a loopback, I did a loopback in Slough because I don't want to be in Slough. You have to put a loopback in to make sure it doesn't blind out all the other signals. But this works. Their CLI thing identified the signal as 1 to 32 gigabit, which of course, much slower than that. But it tried. It can tell the difference. And yeah, so got it all rigged up in LD6, and it didn't work. So I set up the test rig inside that data center using multimode to confirm that everything works, swapped in the DWDM optic, and it just didn't work. So it turns out the DWDM optics have a much higher bar for how slow you can drive them. So this is using the signal generator on my scope. If you sort of wobble around the square wave frequency, you can see that the signal is a bit messed up. So for example, at 3 megahertz, the optic does work, but the signal is not very square. It's got a dip in it. Ignore the ringing. This is not the most pure electrical setup, so I think it mostly works. But yeah, the square wave is not very square at 3 megahertz. I mean, all of this signal is so far out of spec of what these things are supposed to be doing, it's kind of a miracle any of this works. But this is a problem if we want to actually transmit. It becomes stable-ish at 6 or so megahertz, but our toslink signal is about 2 megahertz, which means that this optic, which is the only optic I had, is not going to work. Why? So it's really hard to find out the chips that are inside optics. If you take them apart, you'll find that they're normally like laser etched off, so you can't even look up the data sheets. If you know what the data sheets are, or if you know what the chip part numbers are, good luck ever finding the data sheets for them. It seems that like the providers for the actual suppliers, are very secretive over what these are capable of. So finding what's going on here is really quite difficult. I suspect the DWM side is using a lot more like digital signals processing and sort of noise reduction to make this work, and this is colliding with the fact that I'm clocking something, well, this thing is expecting 10 gig, and I'm feeding it, 6 megabits of signal or less. So it's not surprising that this is not working, but it's also kind of surprising it's not working. I think I was talking to some people, and they were speculating that maybe if you buy a much slower 1 gig or find some like old STM optic that happens to run in DWM, this would work. But who knows? Maybe one of the vendor optics out here, or optical vendors, have more ideas, and in which case I would love to hear them in the Q&A round. Some future pointless innovation. So if the SFP didn't have the line drivers in it, obviously you could just drive it directly with audio and send the full raw audio in its glory. You would probably also burn the laser out if you did this. But I hear this is basically how RF over fiber works. I'm not sure. Couldn't find much information on that. It is also tempting to attach a dial-up modem on both sides. This would probably be the biggest waste of optical bandwidth you could possibly do. That's 100 gigahertz of optical channel to send 40 kilobits a second. It would also really confuse an intelligence agency, I think. So yes, to conclude, you can send low-speed signals over most SFP optics. Most optics I found started working at 150 kilohertz, which is easy. But also it means that you can't send things like UART over it. You can't just stick your serial port in it because there are parts of the times when your serial port is doing nothing, and that will do weird stuff. So you do need a consistent signal. Some of them you can send very far. I mean, 1310, you can send 10 kilometers, apparently. But there's not a good reason to do this. There are many good, obviously very good options outside of that now. You have Dante, you have, for audio at least, you have the other standardized one. There are Ethernet serial solutions. Don't actually do this. But I now know a lot more about optical transmission and general inner workings of how optics work. And hopefully, maybe you do too. Thank you very much. Are there any questions? Oh, you're good.
There is but one question. Anton Capella, 5nines again. Hello. Love SPDIF, Toslink. Since you're in that right part of the world for AES and EBU being a thing, did you try those?
No.
Okay. You want to?
I mean, it's tempting. I think this would work, though, right? As long as it's a serial signal.
Absolutely.
And it has like base clocking, this will work, no problem.
Well, so the curiosity I had, the question for you was, did you explore things that weren't biphase keyed? Because, I mean, SPDIF, is not exactly just like on-off key stuff, which I think most of these PLLs expect, rather, and whatever the line driver interface from that LVDS point forward does in the module. So I'm curious if you did try anything that's not like biphase, just straight up on-off keyed binary stuff.
So SPDIF, so if you take the optical side of SPDIF, that is just on-off.
Oh, okay.
It's just biphase. And so, if you take the coax output, it does something a little bit weirder. Just simply use the optical side or tap the optical side, and I mean, in theory, you could just make a device that takes the actual red LED side and just convert it directly into 10 kilometer, 40 kilometer capable ones, which would be a funnier device, actually.
Right.
It's like, who needs this device? If you need it,
Okay, second question. Why didn't you make it into a guitar pedal yet?
Sorry?
Why did you not make it into a guitar pedal yet?
Oh, that's a good point. Send it down a drum of fiber for a nice delay effect.
Or loss? I mean, Glitchcore loves this stuff. Also a very Euro-sounding thing.
Yeah. Authentic electronic music.
Thank you. Great presentation.
But you're not done yet.
All right.
Mr. Voidy, anything? Mr. Seastrom.
Hi, Rob. Is this on?
Yes.
It is. Okay. Rob Seastrom. Many affiliations, but the one that most people here don't know, except for people like Alex, is also an amateur radio operator. I was wondering if you had torn down, we're interested in both galvanic isolation and lack of RFI. And once you start getting up to 150 kilohertz, well, the harmonics get us.
The signal starts leaving the trace.
Right. So I was wondering if you had done any teardowns of these SFPs to see if you could just drive the LED and the receiver directly. Have you gone down that rabbit hole?
Yeah, I sort of mentioned on this. I'm pretty sure this is how RF over fiber optics work, because they're like a very different class of module. And I think
Right.
basically,
But yeah, I'm interested in driving these at basically audio frequency speeds.
yeah. So this is why I say that. I think RF over fiber for the satellite TV injection stuff in apartment buildings or whatever that they commonly use now, I think is literally very much that stuff that you're looking for. I don't know for sure because there was very little documentation about these systems, or at least ones that would send me.
Yeah, you're correct. It's up around the DWDM, the 1600.
No, but the actual signal coming in is like RF compatible, so you
It's
can
the
probably
same
get
thing.
away with this. Yeah.
We'll talk later.
Yeah.
Thank you.
Okay, next, who I actually don't know.
Hi, I'm Jonathan from Metro Optic. I dabble into electronics and things like that. I was actually wondering if you tried pushing a carrier signal like 6 megahertz and differential signal into the optic and see if it would trigger like the 10 gig or 1 gig minimum that you need to do. Have you thought about that? Just feeding it a carrier signal and altering the bits so that your signal goes through at the other end.
Sorry, I didn't quite hear.
Okay, so if you like pour like let's say 1 megahertz carrier signal,
Yeah.
which is basically just on off every quarter of a tenth of a second.
Yep.
So it basically just gives a steady bit rate, and then you dip where you have signal, so you can differentiate it at the other end because you're supposed to get like a steady bit stream.
Yeah.
Have you tried that, or have you thought about it?
Yeah.
Anyway.
I had a slide. Well, I had some slides which I cut out, which is basically trying to do latency testing, even though the optic didn't work at the expected speeds. I cut it out because obviously it doesn't feel like a win. We didn't get 140 kilometer toslink. We were so close, but we did not get 140 kilometer toslink, intercity toslink.
All right. Well, it's interesting. I mean, we do we do optical transport and things like that, and we don't really spend the time thinking how it works. It just does. We know the specifics.
Yeah.
Like, okay, well, you need to do that, and in order to achieve this, you can't amplify it that way or that way. But it's always interesting to see like somebody like try to hack into it and do other weird things with it. So thank you, Ben.
Thank you very much.
Okay, Mike, last call. My snarky side comment is, have you considered using 100 megabit or 10 megabit optics?
Do they make 10 megabit SFP optics? I couldn't find any for the literature, but I definitely seen 100 meg ones. The problem is you can't find them in DWDM variants. Either that or like all the manufacturers that used to make this obviously don't make this anymore.
They don't make them anymore, but they used to.
If anybody has some in the spare parts bin, I would love to talk to you.
And I'm sure Ken would say that you really just want to run Dante and be done with.
Oh yeah, absolutely. Don't actually do this. But
Okay.
you could.
Ben?
The important part is you can.
Yes, that was really interesting because, as RS mentioned, I am also a ham, and I used to work in recording studios. This is stuff that's really cool for me. Thank you very much.
Thank you.
Let's give Ben a big round of applause.